Hi everyone, my name is TTJ Kepsi Richard and welcome to my YouTube channel. Please remember to subscribe to the YouTube channel and click on the notification bell so that if I post a video, you'll be the first to receive it. Today our discussion on ordinary differential equation is the continuation of finding solution to first order ordinary differential equation. And remember I told you that first order ordinary differential equations is either separable or non-separable. Last, we talked about how to find solution to the separable ones. If you have not watched that video, please go to YouTube and search for the TJ Kepsi Richard and watch solutions to first order separable ordinary differential equations. Today, our discussion will be shifted to the non-separable or the inseparable ones. Before I start things, an ordinary differential equation is inseparable if we cannot separate them. Thus, we can't separate the dependent variable with respect to its derivative and the independent variable with respect to its derivative. If it is inseparable, two things happens. It's either homogeneous or non-homogeneous. So before this video ends today, I will take you through how to determine if a differential equation is homogeneous or how to determine if a function is homogeneous. Then we'll try to find solutions to homogeneous first order ordinary differential equation. This is an interesting discussion. Come with me. So, as I told you, we will learn how to determine if a function is homogeneous. Then, if a differential equation is homogeneous, we'll be able to identify. And we are going to borrow a very essential theory. That theory is Euler's theory. Euler's theory. So Euler's theory on homogeneous function states that a function f which is dependent on two or more variables, that's x, y, and continuous, is said to be homogeneous to the nth degree if for all values of the parameter lambda, f of lambda x, lambda y, lambda z to infinity is equal to lambda exponent n bracket x, y, z. This is very abstract. Let me explain it in a layman definition to you. So, Euler is trying to tell us that to determine if a function is homogeneous, introduce a parameter which is lambda to affect all the independent variables, that's x, y, z, to affect it. Substitute into the function. If you substitute into the function, try to factor out a common parameter or a common value of lambda. If you get the function back, then it is homogeneous. If you did not get a function back, then it is inhomogeneous. We will try to solve a question on this so that you get a concept. So, there is a question here. They say, determine whether or not the function f, which is dependent on x and y, equal to x squared plus y squared, is homogeneous. Is homogeneous. So, what is Euler trying to tell us? He said, introduce the parameter lambda. So now let's write the function first. The function is this x squared plus y squared. So Euler said introduce another parameter, that's lambda, to affect the independent variables. So we have lambda x, lambda y. So in place of x, we put lambda x this time around. And in place of y, we put lambda y. So we have lambda x all squared plus lambda y all squared. I hope you get that. So we simplify, we get lambda squared x squared plus lambda squared y squared. Now what is common to these two? You see that lambda squared is common. We can bring it out. So lambda squared out, x squared plus y squared. The question is, what is here? Is it the same as the function? If the answer is yes, then the function is homogeneous. Therefore, we said the function is homogeneous to degree 2. To the degree 2. So the function is homogeneous to the degree 2. I hope you get this concept. We'll solve one more question to determine if a function is homogeneous or not homogeneous. So look at this. They say determine whether or not the function f, which is dependent on x and y, is equal to x minus 3y over x plus y is homogeneous. So what's our function? Our function x, which f, which is dependent on x and y, is x minus 3y over x plus y. So what is lambda telling us? Introduce the parameter x, parameter lambda to affect the independent variables. So any place we see x, we put lambda x. Any place we see y, we put lambda y. So what are we having? We have lambda x minus 3 lambda y. All over, what is common here? We have, okay, so in place of x, lambda x plus lambda y. So I hope you get that when we see x, we put lambda x, and when we see y, we put lambda y. So in place of x, lambda x minus 3y, y, so lambda y, x is here, so lambda x plus lambda y. Then try to factor out the common parameter, that's lambda. So, but before that, let's try to simplify this. So we get lambda x minus 3 lambda y all over lambda x plus lambda y. So what is common here? Lambda is common, so we'll bring it out. What is left? You have x minus 3y all over. What is common here? Lambda is common again. What is left? X plus y. So remember the exponent of lambda here is 1, and the exponent of lambda here is also 1. So we can use the indices, the law of indices. So we have lambda, when we send it there, remember this is 1, this is 1. When we send it there, it becomes minus. So 1 minus 1. Then we have x minus 3y over x plus y. So lambda, 1 minus 1 is 0. And lambda exponent 0 is 1. So we have lambda exponent 0 bracket x minus 3y over x plus y. Okay, so after we simplify, ask yourself, did you get a function back? Look at that, x minus 3y over x plus y is the same. If it is the same, then we say this function is homogeneous to the degree 0. It's homogeneous to degree 0. I hope you get this concept. I hope you get this concept. So if a function is given to you and you want to determine whether it is homogeneous, you use the Euler's theory of homogeneous function to determine that. We'll solve one more question on it so that you come abreast with how to determine if a function is homogeneous. Then we try to find solution to first order ordinary homogeneous differential equations. So come with me. So we'll solve one more question on how to determine if a function is homogeneous. Then we'll try to find solutions to the homogeneous first order ordinary differential equations. So the function f, which is dependent on x and y, is x cubed plus 2y squared. So we introduce the parameter lambda to affect the independent. So any place we see x, we put lambda x. Any place you see y, we put lambda y. So we have lambda x cubed plus 2 lambda y squared. So let's simplify this and see. So we have lambda cubed x cubed plus 2 lambda squared y squared. Now we factor out a common parameter. What is a common parameter? It's like lambda squared. So we bring lambda squared out. So lambda squared out, what will be left here? We'll be left with lambda x cubed plus 2y squared. Now check this function. Is it the same as this? No. If it is not the same, then we say this function is not homogeneous. It's not homogeneous. So the function is not homogeneous. It's not homogeneous. I hope you understand these things. You understand these things. So the next step is how to solve first order ordinary differential equations that are homogeneous. So come with me. So our next step is how to find solutions to homogeneous first order ordinary differential equations. So before that, we said a differential equation is said to be homogeneous if each term has the same degree. So you check each of the terms with respect to the dependent and the independent differentials. If they are the same, then we say that ordinary differential equation is homogeneous. Now, before we come back to this, look at the first example we solved to determine if a function is homogeneous using Euler's theory. Look at the first term here, the degree is 2. This one, the second term here, the degree is 2. So the degree of each of these terms are the same. So you realize that when we solve this, the function was homogeneous. Look at this one too. Check the degree here is 1. The degree here is 1. Fine. Look at the degree here is 1. The degree here is 1. So they are the same. Each of the term, the degree is 1. So we're able to determine, we were able to know that this function was homogeneous when we use the Euler's theory. Now look at this one. Look at the degree here, 3. The degree here, 2. The degrees of the terms are not the same. So you realize that it will be inhomogeneous. It will be inhomogeneous or non-homogeneous. Now, what we are saying is that a differential equation is said to be homogeneous if each of the terms has the same degree. This is what we are trying to say. So let's look at this differential equation. Look at this. Remember, this cannot be separated. It's non-separable because you can't separate this y square from it. So, if let's say, look at the term here attached to the dx, the degree is 2. The term here, the degree is 2. Look at the term here attached to the dy. Look at this, the degree is 1, the degree is 1. Then, automatically, no one should tell you that this ordinary differential equation is homogeneous. So I hope you can identify it in a quick way. If you are able to identify, then we'll come to the solution, how to solve it. Now, before we start things off, I want to explain something. How you know automatically that you can't separate. Now, look at this function. Look at this differential equation. You see that the dependent and independent variable are multiplying. Can we separate? Yes, we can. Look at it. We can separate this to be. So we just divide both sides by y. So we get 1 over y dy. And to be equal to 6x squared dx. If you separate, it's easy to separate. Look at, so this one is multiplied, easy to separate. This one is divided. Can we separate? The question is, the answer is yes, we can. So when we cross multiply this, we know we can get x dy equal to y dx. What do? We divide both sides by xy. So when we do that, we get 1 over y dy equal to 1 over x dx. You see that we were easy to separate. So it was multiplying, the dependent and the independent, we were able to separate. It was dividing, the dependent and the independent, we were able to separate. Now they are adding. They are adding. Can we separate? Look at this. You can't separate this. You can't. Because you can't separate this y from the dx. You can't. So when it is adding, you see that the dependent and the independent is adding. And you can't factor out any of them. You see that it is inseparable. You can't separate it. You can't. So you realize that when it is multiplying and dividing, we can be able to separate them. We can be able to separate them. But when it is adding or maybe subtracting, we can't separate them. We can't separate them. So remember, division and multiplication can be separated. We are going to use that idea to find solutions to homogeneous first order ordinary differential equations. So I want us to get all the necessary tools so that when we come to the solution, we will not have problem. Now remember, we said if it is multiplying or dividing, they are easy to separate. So after you determine that an ordinary differential equation is homogeneous, you introduce one parameter or a variable known as v. And you let the v be equal to the dependent variable divided by the independent. So we assume that they are dividing. Okay? When they are dividing, you know we can let y to be equal to vx. So any place we see y, we put vx. Correct. Now remember, in our ordinary differential equation, we'll have dy. We will have dy. So we need to get that dy. We need to change or substitute dy into the equation to change the whole system of equation to v and x. If you do that, you will see what will happen. Now, how do we do that? We can differentiate this y. You see, the v and the x are multiplying. When they are multiplying, what do we use? We use product rule. So what does product rule say? It says keep v, differentiate x. Keep x, differentiate v. So we said our dy will be equal to v dx. That's I keep v and differentiated x. Plus, now I'll keep my x and differentiate v. So we'll get x dv. Now, after you substitute this, dy equal to that, and y equal to vx into your homogeneous first order ordinary differential equation, bam, it will become easy to be separated. It works like magic. After you substitute these two things, it will be easy to be separated. So we'll take example questions and I'll take you through how to solve them. So come with me. So we'll solve a first example on that. The question says solve the first order differential equation x squared plus y squared dx. So there is dx here. Minus 2xy dy equal to 0. So, first, what's the first thing to do? You check whether you can separate it. But let me tell you, when they are adding, see, the dependent and the independent is adding, and you can't factor out. Automatically, you should know they are not separable. I told you this. Now, the next thing is that check whether the degree of each of the terms are the same. So we can send this one here. So what's the degree here? 2. The degree here 2. Good. What's the degree here? 1. The degree here 1. Then it is homogeneous. It is homogeneous. So immediately you're able to determine it is homogeneous. You introduce that parameter v. So you say let v to be equal to y over x. You introduce that parameter. So after you let the v to be equal to y over x, that's the dependent over the independent, we are going to change the system of this equation from the dependent to vanish. We'll let it go away. So we are going to make this dependent the subject. So y will be equal to vx. One will cross multiply. What's the next thing? We try to differentiate. So we have y. Now we need dy. So we need to differentiate. So our dy will be equal to, remember we'll keep v and differentiate x dx. Plus now we'll keep x and differentiate v. So x dv. Now we are going to substitute this and this into our differential equation. Bam! It will become separable. It will become separable. So check things out. Let me copy our differential equation here. We have x squared plus y squared dx is equal to 2xy dy. So remember, our y is equal to vx when the v was y over x. Is here, check, is here. So our y is equal, when v is equal to y over x, y equal to vx. So we have our y. Now we find dy. Our dy is equal to, we keep v, differentiate x, plus keep x, differentiate v. Now we substitute this and this into our system of equation. Now, any place we see y, we put vx. Any place we see dy, we put the whole of that. So we have x squared plus, so vx all square dx is equal to 2x. Remember our y is vx. So vx, then times our dy. dy is this. That's v dx plus x dv. I hope you get that. What do? We expand. So let's polish this. We have x squared plus v squared x squared ds is equal to 2x squared v times v dx plus x dv. I hope you get that. Now we let we distribute the dx over them. So get s squared dx plus v squared s squared dx. S will multiply this, multiply that. Is equal to, this will also multiply the whole of that. This times this will be 2s squared v squared dx plus 2s cubed. Remember that? V dv. I hope you get that. I hope you get that. Now what's the next thing? We'll bring all the ds to one side and all the dv to the other side. So you have s squared dx plus v squared s squared dx. There is a ds here, so we bring it to 2s squared v squared dx is equal to 2s cubed v dv. What's the next thing we need to do? We need to factor out dx. You see that is common. So we have s squared. When factor out, we'll be left with s squared plus v squared s squared ds will go minus 2s squared v squared. Then dx is equal to 2s cubed v dv. What is common in there? You see that s squared is common to all of them. We bring it out. So s squared out, what is left here? 1 plus v squared minus 2v squared. You get that? ds. So s squared is out, v squared. S squared is out, we left with 2v squared. Is equal to 2s cubed v dv. Or in leading s to separate it. So s squared, you can v squared minus 2v squared is minus v squared. You get that? dx is equal to 2s cubed v dv. Now what do we want it to go there? We want 1 minus v squared to go there. And we want s cubed to come here. So we divide both sides by that. We divide both sides. So here divided by s cubed 1 minus v squared. Here divided by s cubed 1 minus v squared. So this will divide that. We'll be left with s squared over s cubed ds. So this s cubed will go away. So we have 2v dv all over 1 minus v squared. I hope you get that. I hope you get that. We can polish this. We can polish it. But let's copy this to this side of the board so that we continue. So we have s squared over s cubed dx is equal to 2v dv over 1 minus v squared. Yes. So we can polish it. We have 1 over x. Remember, this can divide that. ds is equal to 2v dv over 1 minus v squared. So we're able to separate. We're able to separate. So this is the powerful aspect of this. Immediately you substitute the y and the dy, it will become easy to separate. So what's the next thing? To get a function, we integrate both sides. So we integrate both sides of the function. Remember, the differential, the integral of 1 over s is linear, so we don't have problem. Now what of this? See, anytime if you differentiate this, a function here, you will get what is there at the top. We can use integration by substitution. We use integration by substitution. So I will show you how to do the integration by substitution, then we take it from there. So look at it. So let's take this alone to integrate. Look at it, 1 minus v squared. So what we will let our u to be equal to this 1 minus v squared. Then we differentiate this du over dv. So when we differentiate it, we get minus 2v. Now we send it there. So we have our du will be equal to minus 2v dv. Now we need 2v dv. So what do? We divide both sides by negative 1. So we get negative du is equal to 2v dv. Now, any place we see 2v dv, we'll put negative du. I hope you get that. And any place, so 1 minus v squared, in place of that, we'll put u, so that we can integrate. So look at it. You can integrate this. So the integral of 2v dv over 1 minus v square will be equal to the integral of, so in place of this, we'll put negative du over, in place of d, we'll put u. What can we do again? We can factor out our negative out, since it is constant. So we factor it, our negative out, 1 over u du. 1 over u du. I hope you get that. So what will be the integral of 1 over u du? The integral of 1 over u is ln u. So we have negative ln u. Remember, plus our constant. But we don't have u here. So we replace the u. Remember, we said the u should be 1 minus v squared. So we replace it. So this inertia will be equal to negative ln 1 minus v squared plus c. So now we know the integral of this to be this, and we know the integral of this to be ln x. So we just substitute, then we will take it from there. Okay, so remember we said that the integral of this, we were able to find the integral of this to be this. So we just substitute this in place of the integral of that. So the integral of this, remember, is also ln x. I know you are convenient with it. It's equal to negative ln 1 minus v squared plus c. What do? We can bring this here. So ln x plus ln 1 minus v squared equal to c. You can rewrite this. Remember, this is log. So when two logs are adding with the same base, we just multiply them and repeat the base and repeat the log. V squared. So we can write this as that is equal to c. What's the next thing? Since this is constant, we can let the constant c to be equal to ln k. So in place of c, we put ln k. So we have ln x 1 minus v squared is equal to ln k. Now, since there is ln on both sides, we can say x 1 minus v squared is equal to k. Is that what it is? So what's the next thing? Remember, in our initial equation given to us, this, check out this. You will see that there is no v in it, but we said we should let v to be equal to y over x, if you can remember. So in place of v, we just put that. So we have x bracket 1 minus y over x in place of v all squared will be equal to our constant k. So what next? X bracket 1 minus y squared over x squared is equal to k. You can just let x multiply that. We expand. So remember, we have x 1 minus y squared over x squared is equal to k, right? So this times this will give us x. This times this, remember the x will reduce this by 1. So y squared over x is equal to k. What's the next thing? We can multiply through by x. So we get x squared minus x times this will be x squared. X times this will just be y squared is equal to kx. We can make y squared a subject. So our y squared can be equal to x squared. So we send this and bring it minus kx. Then this becomes our function. So this is our general solution. If we are given any condition, we can find a specific or particular solution. I hope you understand this. We'll solve one more question on this so that we take it from there. Okay, so we will solve the second question on the homogeneous. So they say solve the first order differential equation 2 bracket x plus 2y dx plus y minus x dy equal to 0, given that y of 1 is equal to 0. So remember, this one, conditions are given to us. So we are going to get a particular solution. We won't get a general solution. Since conditions are given, we'll get a particular solution. So now let's see how we solve that. So remember, this 2 bracket x plus 2y dx plus y minus x dy is equal to 0. Can we separate this? We can't separate. Look at it. We can't separate. So it is inseparable. Is it homogeneous? Determine that we can multiply this off. So we get 2x plus 4y, okay, dx. Then we send this one here, negative y minus x dy. Can we, is it homogeneous? The degree here 1, degree here 1, perfect. Degree here 1, degree here 1, perfect. So it is homogeneous. It is homogeneous. So we can solve that. So let's polish it before we start. Dx. So since this is multiplying, we can rewrite this as x minus y dy. That's when negative multiply y, we get minus y. When negative multiply the negative s, we get positive. So if it is homogeneous, the next thing is that you try to make it separable. How do we try to make it separable? You let v to be equal to y over x. So what next? If v is equal to y over x, our y will be equal to vx. Very, very important. We differentiate the y now, we get dy will be equal to, this is product, v dx plus x dv. Now we substitute this and this into our system of equation, into the ordinary differential equation. Then bam, it will become separable. So now let's see, we substitute that. So any place we see x, any place we see y, we put vx. Any place we see dy, we put x, v dx plus x dv. So we go. So we have 2x plus 4. In place of y, we put vx there. This vx. So dx is equal to x minus v, so we'll put v, x minus y, so we'll put vx, bracket. Then in place of this, in place of the dy, we'll put the whole of that. That's v dx plus x dv. I hope you get that. So we substitute. Now what is the next thing? We try to multiply things off and expand. So now what do we have? We are having 2x plus 4y. Okay, 2x, we substitute already. So 2x plus 4 vx dx is equal to x minus vx, then v dx plus x dv. So we expand. This will multiply this, we get 2x dx. This multiply this, we get 4vx dx. Then please take your time in multiplying this very well. So x will multiply this, we get vx dx. X multiply this, we get s squared dv. I hope you get that. Now this will multiply this, it will be v squared x dx minus. Then this will multiply this minus vx squared dv. Now what's the next thing? We bring all dx to one side and all dv to the other side. So we have 2x dx plus 4vx dx. There is a dx here, so we bring it. So vx dx. There is another dx here. Remember it's negative, so we can plus v squared s dx. And to be equal to, we have s squared dv minus vs squared dv. I hope you get that. So what's the next thing? We try to bring out the dx. We bring out the dx. So when we bring out dx here, we'll be left with 2x. We bring it out here, we'll be left with 4vx. We bring out here, we'll be left with vx. When we bring it out here, we'll be left with v squared x. Or dx is equal to, now we can bring the v out, so we get x squared minus vx squared dv. What's the next thing? We try to see what is common again. You realize that x is common, so we bring it out. X out, what will be left here? 2. X out 4v, x out v, x out plus v squared dx. And to be equal to, what is common here? X squared is common, bring it out. Then 1 minus v the V. So we can simplify this. See, 4V cancel try this. So 4V minus V will be 3V plus V squared ds equal to S bracket 1 minus V dV. So can we? So this place is square. So now can we separate? Here we can separate. We divide. We let the S come here and this go there. You can separate by dividing both sides by that. We can rearrange this in order of our magnitude. So we can say X over S squared dx will be equal to 1 minus V over, let's arrange this, so V squared plus 3V plus 2 dV. So we're able to separate. So this is very magic. After you substitute those things, it will become separable. So let's polish this. You have 1 over X dx is equal to 1 minus V all over V squared plus 3V plus 2 dV. Now, how do we do to get our function back? We integrate both sides, right? We integrate both sides. The integral of this is easy to find. In the next part of this. See, you see that this is quadratic equation. So how can we integrate this? We have to first resolve this into partial fraction. When we resolve this into partial fraction, that's you determine whether the type of partial fraction, you know, type 1, type 2, type 3, type 4. If this is simplifiable, you know that is type 1. And I'm sure this will be simplifiable, so we'll use a type 1. So first, I'll pull this out and try to integrate that first. Then we'll take it from there. So now, let's try to integrate our 1 minus V all over V squared plus 3V plus 2 dV. We are trying to integrate that. So first off, I'll solve this to see if it is solvable. So V squared plus 3V plus 2. So remember how to solve quadratic equations. We say you find two factors. One you add, you get 3V. One you multiply, you get 2. So that will be 1 and 2. 2V. So V plus 2V plus 2. So 1 plus 2 give you 3. 1 times 2 is 2. So we factor out the common. So V out, we have V plus 1. Plus 2 out, we have V plus 1. Then V plus 1 is common, we bring it out, we will left with V plus 2. I know you can do this. So this, our 1 minus V over V squared plus 3V plus 2 will be the same as 1 minus V over V plus 1, V plus 2. So this is type 1. So we said this should be equivalent to A over V plus 1 plus B over V plus 2. So if that is equivalent, we can resolve this. Place in exam, this can be sideway for you to not to make your solution so lengthy. It can be sideway. So now the LCM here is V plus 1, then V plus 2. So we have A, if this goes here, V plus 1, plus 2, this will divide out, we'll be left with V plus 2, plus B, V plus 1. I know you know all these things. So we say our 1 minus V all over V plus 1, V plus 2 will be equivalent to, so you know the denominators are the same, so the numerator to be equivalent. A bracket V plus 2 plus B bracket V plus 1. I hope you get that. What's the next thing? So since we know, so please, this can be, that's 1 minus V actually. Since they are the same, we just bring this to be equivalent. So first check. We'll let V to be equal to minus 2. You know this. So we get 1. So when V is equal to minus 2, what do we have? We have 1 minus 2 equal to A minus 2 plus 2 plus B minus 2 plus 1. So this will be 3 equal to, this will be 0, remember. So the whole of that will be 0. Minus 2 plus 1 is minus 1 times b will be minus b. So our b is equal to minus 3. I hope you get that. We'll try to find a2. Then our board is full. I will try to find a2. Then we take it from there. Okay, so we had our value for b. Now we find a. So it will let v to be equal to minus 1. So 1 minus minus 1 will be equal to a minus 1 plus 2 plus b minus 1 plus 1. So we get 2 equal to minus 1 plus 1 is 1. 1 times a is a. Then this will be 0. So our a is equal to 1. Is equal to 2, sorry. Our a is equal to 2. Now, you know that this is what we were trying to resolve. This. That's v 1 minus v over v squared plus 3v plus 2. So it will be equivalent to our a is 2. So 2 over v plus 1. If you remember very well, our b is negative 3. So negative 3 over v plus 2. I hope you get that. I hope you get that. So our integral 1 minus v over v squared plus 3v plus 2 dv will just be equal to the integral of this 2 over v plus 1 minus 3 over v plus 2 dv. So we can integrate this 10 by 10. So we have integral of 2 over v plus 1 dv minus the integral of 3 over v plus 2 dv. Remember, these are constant. We can just bring them out. So we get 2 integral of 1 over v plus 1 dv minus integral minus 3 integral of 1 over v plus 2. So when we integrate this, remember this will be ln. So 2 ln v plus 1 minus 3 ln v plus 2 plus c. Our constant of integration. So remember, we're having the integral of 1 over x dx and to be equal to, and is equal to the integral of 1 minus v all over v squared plus 3v plus 2 dv. You know this is ln x, so ln x, then this is this, so we have 2 ln x plus 1 minus 3 ln x plus 2 plus our constant of integration. Remember, we can rewrite this as ln x equal to ln x plus 2 all squared minus ln x plus 2 cube plus c. We are using the laws. So ln x, another law, so ln, this will be ln x plus, sorry, this is 1, x plus 1 squared all over x plus, so is v rather, not x. Very, very important. Is v. This place is v. Is v. So v. So let's use v. So this will be v plus 2 exponent 3 plus our constant c. We can bring this constant here. We can bring the constant there. So what we have? We will have ln x minus c is equal to ln v plus 1 squared over v plus 2 cube. Yes. So we let c to be equal to another ln function of k. So our ln x minus ln k will be equal to ln v plus 1 squared over v plus 2 whole cube. What we have? We can rewrite this as ln x over k, since they are subtracting, is equal to ln v plus 1 squared over v plus 2 cube. Yes. So since they are the same, we can say x over k. Ln is both sides, is equal to v plus 1 all squared over v plus 2 all cube. So we can cross multiply. Our x can be equal to, we can cross multiply x times this v plus 2 cube will be equal to k bracket v plus 1 squared. And remember, our v is equal to y over x. So we substitute this into the place of v. So our s will be equal to our s bracket y over in place of v we put that plus 2 quick is equal to k bracket y over x plus 1 squared. So what do we do? We just substitute our initial our boundary condition given to us, then we'll get, so this is our general equation. We substitute the boundary condition to get what? The specific solution. The specific solution. Remember the boundary condition was y of 1 is equal to 0. So our y is 0 and x is 1. We substitute to get that. So this is where we reach. Please, this is not lending. It's just that I'm trying to make sure you understand things. If it is exam, you can skip the partial resolving place. You can skip it. That you solve it as a side where you can bring it. So it's not lending. Don't let this discourage you. This is a very, very interesting thing. So please, don't let it discourage. So we just substitute our boundary conditions. So remember our s is, no, it was like this. It was like this, if you remember very well. So y of 1 is equal to 0. So s is 1 and y is 0, if you remember very well. So now in place of s, we put 1, in place of y, we put 0. So we get 1 bracket 0 over 1 plus 2k is equal to k bracket 0 over 1 plus 1 squared. So 1 multiply this with this thing. 0 over 1 is 0. 0 plus 2 is 2. So 2k is equal to k bracket 0 over 1, 0 plus 1 is 1 squared. 2 cube is 8 and 1 square is 1. So k. Our constant is 8. So we just substitute our constant to this to get our specific solution. So our specific solution will be y bracket y over x plus 2 cube is equal to 8 bracket y over x plus 1 square. This becomes our specific solution. I hope you understand this. Play over the video and you get a concept. Please remember to subscribe to the YouTube channel and click on the notification bell so that if I post a video, you'll be the first to receive it. Our next video will be on finding solution to non-homogeneous first order ordinary differential equations. Until then, bye-bye.